All right, well, good morning, everyone. My name is Brooke Finlay, and today I will be explaining a hypothetical asteroid impact case study in Romania. So before I get into the details of this study, I'm going to explain some of the basics of asteroids and the effects they cause after impact. So near-Earth objects are most often not large enough to make it through Earth's atmosphere, therefore producing airbursts. When they are large enough, they can impact Earth's surface. In order for an asteroid to cause destruction on the surface, it must be larger than 100 meters in diameter. Asteroids of this size usually occur every 10,000 million years. The asteroid we are looking at for this study is between the city scale effects and the regional effects shown on this diagram. Asteroids that do impact the Earth's surface produce first order effects, which include blast wave, thermal radiation, cratering, and ejecta, amongst others. These effects lead to cascading hazards that further damage the surrounding environment. Some examples of cascading hazards include wildfires, hydrophobicity, flooding, dam breaks, and landslides. One chain of events is when the asteroid produces thermal radiation. This then sparks wildfires, which makes the soil hydrophobic and eventually leads to flooding when rainfall occurs. This chain of events is what we have decided to focus on for this hypothetical impact event. This diagram shows the first order and the following cascading hazards that occur from an asteroid impact. When the ground is thermally radiated, the soil erodibility and structure can be affected. This leads to increased hydrophobicity, thus an increase in runoff and post-impact flooding. We derived our scenario from the 2025 Planetary Defense Conference, where it was introduced and discussed. The Planetary Defense Conference is a biannual international multi-agency meeting that discusses a hypothetical impact scenario in depth. Although we are basing this impact event on the risk corridor that was provided, we are not constraining ourselves to the asteroid size limit. This map shows the risk corridor, and as you can see, it runs through Romania. We chose this as our location of interest because the impact is in a largely unpopulated area, the mountains of Romania. So we wanted to see more of the effects of the cascading hazards rather than the first order effects, specifically the flooding and whether it would reach the capital Bucharest and Romania's major port city, Constanța. We used GeoClock to create flood models for various impact locations and rainfall amounts. GeoClock calculates flood depths due to various rainfall levels. This code solves the shallow water equations to model dam break floods and tsunamis. GeoClock does not account for river-based flow, evaporation, transpiration, sediment flux, or infiltration, which creates some uncertainty in this method. We have modeled the hydrophobically damaged area by making every pixel within a specified radius a spring, meaning that it discharges water at a specified rate. This is equivalent to a perfectly circular rainstorm discharging water over the hydrophobically damaged area. Throughout this project, we have asked ourselves, when do we start to care about the size of the asteroid and its impact location? In order to examine these questions, we are varying the impact site and asteroid size. Our variables include the size of the hydrophobic radius, the amount of rain, the length it will rain for, and where along the risk corridor we want to examine. The size of the hydrophobic radius is correlated to the size of the asteroid. So the larger the hydrophobic radius, the larger the asteroid we are dealing with. We have been examining 5 different locations along the risk corridor and using 3 different radius sizes for each location to see when the size of the asteroid and the impact location begin to cause destruction. A radius of 24 kilometers is associated with the 99th percentile case from PDC 25. This radius size correlates to an asteroid with a diameter of 230 meters. A 12-kilometer radius is associated with an asteroid that has a diameter of 200 meters. which is the 95th percentile case in PDC 25. A rainfall event of 4 millimeters per hour for 24 hours corresponds to a likely but severe case. 8 and 16 millimeters per hour for 24 hours corresponds to events that are unlikely with the current climate trend, but should be considered as climate change makes rainfall more severe on a global scale. We chose these sizes and rainfall rates to look at worst case scenarios in order to get an idea of when these events start to become severe enough that they affect mitigation and recovery planning. This map shows the 5 different locations that we chose, which range from the top of the mountainous region to outside of the mountainous region. The radii shown here are associated with an impact location that NASA chose when they were doing their analysis, but it is unrelated to our current project. To analyze our results, we looked at the number of people exposed and affected at each impact location for each radius size and rainfall amount. Our definition of exposed is anyone that was exposed to any level of flooding from getting their feet wet to drowning. Our definition of affected is based on a mortality function to estimate what percentage of people would be considered a fatality. Location 1 is one of the most damaging impact locations. This is because it is upstream from Bucharest. For the worst case scenario at this location, we are getting around 2 million people exposed and 45,000 people affected. The 8 and 16 millimeter per hour rainfall rates with the radius of 24 kilometer runs are less accurate due to errors in how the computation model is processing spatial information. Location 2 is further west of Bucharest, which would explain why the maximum exposed and affected are less than for location 1. Though there are still roughly 1.6 million people exposed to flooding and from an impact at this location. Location 3 is much farther north than location 1. It is not in the same watershed as Bucharest and is located in the mountains near Brazov. So the water gets split between watersheds on either side of the mountain. Thus, a lot of the water is lost in the northwestern region of Romania. The remaining water flows towards Bucharest, but the volume is significantly less than the other locations. Differences in rainfall amount are not as influential as compared to differences in catchment area size. Location 4 is the furthest location south that we chose, and it is in a flat, low-lying valley. This means that the water primarily flows into the Danube River and does not reach high population areas like Bucharest. The results in lower population estimates with exposed being roughly 140,000 and affected being 5.5 thousand in the worst case. Similar to location 3, the rainfall rate is not as influential as the radius size. Location 5 was chosen because of its proximity to location 1, which we knew could have severe effects on the population. This location is in the same watershed as Bucharest, which is neighboring the one location 1 is in. This impact location exposes more people to flooding than all other locations at about 2.3 million, and it affects more people at around 52,000. This is the most severe location we examined. Here we are looking at exposed and affected populations at all locations ordered from north to south for the specific case of a rainfall rate of 4 millimeters per hour and a radius of 24 kilometers. This case represents the most likely worst case scenario, where we are using a rainfall rate that is probable with the current climate trends and a radius that represents the worst case scenario. As you can see, location 1 and location 5 have the most severe effects, which is expected based on them being upstream from Bucharest. Here we are looking at the cumulative exposed and affected population in each location over time for the same scenario as the last slide. One thing you'll notice is that location 5 exposes more people, but location 1 affects more people. This is likely because water in location 5 is spreading out more, thus exposing more people, but with lower mortality. While for location 1, water stays more concentrated, thus exposing less people but with higher mortality. The same can be seen for location 2 and 3. As an example of the potential effects of the cascading hazards, we want to consider societal consequences and how it might affect the geopolitical and societal future of Romania. We want to consider the effects on the supply chain, energy access, building damages, crop failures, geopolitical effects, and many more. Some of the major concerns would be if the flooding reaches Romania's only nuclear power plant, which supplies about 20% of the country's energy. Additionally, Romania's transportation sector, including rail, highways, and maritime transport for both pedestrians and cargo, would be at risk from the secondary effects caused by the impact. This could lead to a significant decrease in Romanian exports and therefore leave long-term effects on their economy. In conclusion, there are a few general trends that reveal the influence of our parameters: radius size, rainfall rate, and location. We observe that as the radius increases, the population becomes more sensitive to the changes in rainfall rate for all of the locations. When the area directly above Bucharest gets hydrophobically damaged, we see a jump in severity. This goes for locations 1 and 5, which are upstream from Bucharest, and location 3 when the radius is large enough. Because the radius of 6 kilometers leads to low severity events, this hazard only becomes significant once the radius is 12 kilometers, which is an asteroid diameter of around 200 meters. These results are preliminary, but give a good idea of what we are examining. While this event is highly unlikely, perfect storms do happen, and it is important to be prepared for when they do.
Thank you so much for that great talk. We have a few minutes left for questions. If anybody has any questions in the room or online. I can start us off. I had a question about how you were some of the future work and the other things that you want to quantify, like effects on the supply chain. I was wondering how you planned to try to quantify that, or if it was going to be more of like a qualitative estimation.
We were mostly going to be looking at like how it was going to affect like transport and if they were able to like get exports out, because the areas we were looking at the impacts were going to impact a very like important railway. So we were going to see like how often that railway is used and if they would easily be able to go around it.
Great, yeah, that makes sense.
So I had a question about how long it's taking your method to like run these types of simulations, because it strikes me that there was a lot of variability depending on where exactly the impact struck, and that if you could run lots and lots of potential locations, if that's a feasible thing with time, that might be helpful.
Do you mean like if we wanted to do more?
Yeah, so if you started at the beginning and say, I want to run this as opposed to at 5 locations, I want to run it at 100 locations. Is that something that's feasible within time constraints of how the method works?
Currently not for me at least, because I'm just here for the summer. So so far we've only been able to do these 5 locations because we are running into a lot of issues and then have to redo it. But yeah, if time allows, it would be nice to look at other locations.
We have a question online from Jim Kasek. Following on effects, some of the cities mentioned I recall as being popular with tourists, such as Brasov. Do your population estimates include possible visitors, and do you think including tourism may change some of your implications?
I was considering, when I was doing my research, I was looking at the tourism. I didn't know it was that like popular. We have not really like considered that in what I talked about, but it would be something to look at for the future, especially if it's a lot of people going there. Yeah.
Totally. Yeah. One more quick question.
Not a question. I was gonna expand on, we actually are using OpenLeaf, so supercomputer, to run GeoClaw And we're currently working on trying to set up a parameter sweep so that we can do a really large number of locations at once. Right now, I think that the models, we're doing about 9 to 16 at once. And it takes about like $3 or $5 for each one to finish.